Well, first I would like to thank the organizers for the invitation to the conference. It's really a great pleasure and also honor to speak here on the occasion of the 70th birthday of Alex Yeremenko, who has been my friend and collaborator for many years. So I will well, the talk will maybe have some similarities with that by Alan Sokal yesterday. By this, I don't mean that it will be as good as his, but the similarity is that it will mainly be about problems. So I will not have any recent results that I will talk about, but I will mainly focus on some problem. And well, but I will also, well, you see some pictures here already, maybe also say a little bit non-mathematical how my collaboration with Alex started. Okay, so starting point of my talk here is a paper which appeared 35 years ago in the proceedings of some semester on dynamical system and ergodic theory at the Banach Center. And the paper here is the following: on the iteration of entire functions by Alex Yeremenko. And well, we are in some sense celebrating the 35th anniversary of this paper, but of course, maybe more important is the anniversary that the author is twice as old as the paper now. And so, happy birthday, Alex. So at that time, he was at in Kharkov at the Institute of Low Temperatures. And I actually visited this institute once on the way to a conference in Sumy in Ukraine. Well, actually, I think I've had mentioned this name Sumy 3 years ago. Maybe only the Ukrainian would have heard this, but nowadays this is unfortunately very different. So that because also, well, Sumy, Kharkiv, they are all under massive attacks. Well, very bad. But okay, so but let's now continue here with this paper. So this paper really had an enormous impact on the further development of transcendental dynamics. So what is transcendental dynamics? It is iteration of entire functions, or more generally, maybe also meromorphic functions. And well, this was one of the very early papers in the area. Of course, there was a paper by Fatou, there was a work of Baker, and which also had a lot of impact, but definitely this one had, and I will want to talk about some of the impact. So we will discuss some developments arising from this paper. So the paper is concerned with the escaping set, which is also the title of my talk. So what is the escaping set? Well, let us look again at the paper. So the escaping set was introduced in this paper by Alex and denoted by I of F. And this is a set of all points where the iterates tend to infinity. So Fn denotes the nth iterate, f of f n times. So this is a set which is introduced in this paper and which we will also study in this paper. So Alex notes that for polynomials, the Julia set is just the boundary of this escaping set. So the Julia set is a set where the iterates do not form a normal family, and this is somehow the main object studied in dynamics. But well, if you are not familiar with it, do not worry about it. It will not really play much of a role. And Alex proved in the paper that this equation, so Julia set is boundary of escaping set, also holds for transcendental entire functions. But the first thing, in order to show that this is true, the first thing to do is one has to show, and this is what he does, that the escaping set is not empty. Once you know that the escaping set is non-empty, it is actually not too hard to show that the escaping set is the, what happens? Yeah, okay, that the escaping set is the, that the Julia set is the boundary of the escaping set. So well, I said this already. So J is the Julia set, and it's the boundary. Well, I saw this paper first in February 1990. I still remember this. David Drazen showed me the paper at a conference in Oberwolfach. So, well, he came with this book from the library. Maybe for the younger generation, yes, there was a time before internet and archive. And so to read math papers, you did actually go to the library. Yeah. Okay. So, and David and picked up this the volume where the paper was and showed it to me. Well, why did he do this? Well, I had given a talk on periodic points of entire functions, so which somehow was one of my first excursions into dynamics. And one tool I had used was Wiemann-Walleyron theory. So we heard about Wiemann-Walleyron theory in Patrick's talk yesterday already. And so, and this is yeah. And the reason David showed me was to show me that I was not the first to use this Wiemann-Walleyron theory in dynamics, because in the paper by Alex I just mentioned, he had also used Wiemann-Walleyron theory. So what is this Wiemann-Walleyron theory? It is the result from Wiemann-Walleyron theory I state here is it's a slightly different statement from that Patrick gave yesterday, and but it essentially it is the same theory. So what you do is you consider a point. What did I? Yeah, you consider a point W. Which has W of R, which has modulus R, and which is a point where the function f takes the maximum on the circle of radius R. So W of R is a point on the circle of radius R where f takes its maximum. And NR, this came up yesterday already. So there it was denoted by nu of R, but this is a central index. This is the index where the maximal term in the power series occurs. So f, you write it as some a n z to the n, and well, because the series converges, a n z to the n tends to 0 as n tends to infinity, and so now you take the term in the series which is maximal, and the index where it is attained. Usually you take the largest index where it is attained. This is called the central index. So the condition up here means that WR is a point where the maximum is taken. And this means if Z is close to the point where the maximum is taken. So how close exactly, do not worry about it. But this is the idea. And then the conclusion is if Z is close to the point where the maximum is taken, then f of Z is Z to the n of R. So Z to the central index times something, essentially. So in this neighborhood of the point W of R, f behaves like a power of Z. So this is the main message. Near the point of maximum modulus, f behaves like a power of Z. Well, not everywhere. There is some exceptional set, but do not worry about it. So, but once you know that f behaves like a power, you can differentiate powers, then you know how the derivative behaves and how higher derivatives behaves. And this was sort of the statement that Patrick was using yesterday. So maybe to remember about Riemann-Wallerand theory is the following. So essentially it says that near a point of maximum modulus, the function behaves like a monomial of large. So what does it mean if you take a small neighborhood of such a point of maximum modulus? Then this is mapped to some large annulus. So let's look at a picture here. So our small neighborhood is the intersection of a sector with an annulus. We take a small sector with the intersection of this with a thin annulus. So what is the image under a large power? The thin annulus becomes a thick annulus, and the small sector, narrow sector, becomes a wide sector. And if the power is large enough, then it's the wide sector is wider or has opening angle bigger than 2 pi. So you have a complete annulus. So the image of the small yellow neighborhood will be a large annulus. Well, now you do the following. In this large annulus, you pick again such a neighborhood. Well, I told you there is an exceptional set, but it turns out the exceptional set is small enough so that if you take, well, you can still find a neighborhood where you can apply the same argument. So this blue neighborhood is mapped to a large annulus drawn in blue here. So, but this blue neighborhood also has a pre-image in the original small neighborhood. So this pre-image now in 2 steps is mapped to the large blue annulus. So, and in the blue annulus, you again take some small neighborhood where this Riemann-Wallerand theory can be applied. Well, this will be mapped to some large annulus, red annulus, which is so large that it doesn't fit into the picture anymore. But again, this red neighborhood has a pre-image first in that blue and then pre-image in that original neighborhood. Well, and now you see if you take this red neighborhood here, so how is it mapped? Well, first it is mapped to the next red neighborhood, then to the other, and then to this big red annulus, which doesn't fit into the picture anymore. And now you see some induction argument, hopefully already. So you continue on doing this, and then inside here, you have a nested sequence of smaller and smaller neighborhoods. There is a point which is in the intersection of all these neighborhoods, and this point will go to infinity under iteration. So this is the argument by Alex to prove that yeah, there are points which tend to infinity under iteration. So I should perhaps also say when David showed me this paper by Alex, well, this was the first time I saw this paper. This was definitely not the first time I heard the name Alex Yeremenko, because, well, Alex was and still is a very big name in Nevalina theory, which was, well, the area where I did my PhD. And so certainly from that area, I knew this name very well, of course, already then. Okay, so this was when I, so far, this was what I said. I knew the name Yeremenko. I then saw this paper on iteration. The first time I met Alex in person was in March 1991. At a workshop in Joensuu, which was organized by Ilpo Leine. And well, Ilpo had, I think the idea was that this was a small workshop, but it actually became then a very small workshop. One reason was that at this time there was the Iraq war, and so some people were afraid to fly because there were some threats that planes would be shot down or whatever. So the small workshop, Ilpoet plant became a very small workshop. And as far as I remember, there were only 4 non-Finnish participants: Alex, his advisor, Alex Goldberg, whom you can see sitting here with Alex enjoying a coffee, and also giving a talk here, and Alex translating the talk. So, and beside them there was Jörg Winkler and from me. On the other hand, well, if a workshop is very small, one result of this is that the interaction between the participants is maybe more intense than it is for a big conference or so. And we really talked a lot in this. So Alex and his advisor Goldberg and I, we shared an apartment, and we talked a lot. Talking a bit complicated. We had no common language. Goldberg spoke Russian, so Goldberg spoke German. So with Goldberg, I spoke German. With Alex, I spoke English, and they spoke Russian. There was only 2 people to talk at the time. So there was a lot of translating, and no, but I think it was a very good and very intense week, and I think Ilpo, your workshop probably contributed also to starting this long-term cooperation, which I have with Alex now. Okay, so well, then 2 years later, there was a possibility to invite visiting lecturers. Sort of, well, I still sort of remember we had this faculty meeting, and they said, well, there is some money for, and I think I was always pretty good in shouting here at such occasions. And so, yes, so I got invite Alex, and he accepted. Well, there was a small obstacle. I still remember his email, and I think what you see now, I think is a full text of the email, which I seem to remember well. So it said, I received my visa. I'm pretty sure that this was the full text of the email. Well, also we could get around this obstacle, and we could still invite him, and so he visited for a couple of weeks.
Could you translate that into Russian, please?
This cannot be translated.
And for the younger people, there was a time before internet, so you could not Google such a sentence. So if you did not have dictionary on your bookshelf, you were lost. Yeah.
So what does that mean for those of us who don't speak German?
Well, you're not allowed to work. No working permit.
Okay.
I wrote an email to Alex saying, well, it means no working permit, and I will somehow, well, and he just wrote back, this is what I guessed. But anyway, someone put it clear that the money, that he was not for work, but for travel and so far. Okay, so the Alex stayed with us. I think it was 3 weeks or so. He said, my wife and I lived in Düren, which is between Aachen, where I worked, and Cologne, where she worked. And so Alex stayed with us there. So here you see him reading a book in the garden. By the way, this is The Man Who Knew Infinity, a biography of Ramanujan. And so we're also doing some excursions. So there is some museum with farmhouses and so nearby. You can see us there. But we did not only do sightseeing, we also did a lot of work, and it actually was during this stay that we wrote our first paper. So the same year, I also visited Alex in West Lafayette at Purdue University. So you see us here with his colleague Alexander Frentov. And well, anyway, so these years, 91, 93, were the start of a long-term collaboration, so which also continued after I moved from Aachen via Berlin to Kiel. And so also there, he was one of the first visitors I had in Kiel. And then in 2000, he obtained the Humboldt Prize. The Humboldt Prize is a prize which essentially also the idea is that it gives you money to visit Germany for scientific contacts. And well, and Alex, I think he seems to have liked it. So because since then, essentially, he has come to Kiel every year, with very few exceptions. So one exception was COVID, of course. The other exception, unfortunately, was also this year. So he couldn't come to this conference, but it was also planned that he would be in Kiel before the conference, but this unfortunately also didn't work out. Okay, so far for the pictures here that and let us now go back to the, so here, of course, here in Kiel, you see we are with one of the organizers there. So, but back to the paper. The paper became famous not only because of the results that were proved there, but also because of a conjecture. So the conjecture was the following. Well, he writes, it is plausible that the set IF has no bounded connected components. We shall prove a weaker statement, so he proves that the closure of IF has no bounded components. So this conjecture really became one of the central problems in transcendental dynamics. So it really initiated a lot of research. So there were many papers concerned with it, either directly or maybe with this conjecture in the background somehow. Now, this conjecture was recently solved by David Marti-Pété, Lasse Rempe, and James Waterman. They constructed a counterexample. And well, James will talk about this afternoon. So I will only say that they constructed a counterexample to this conjecture. And well, you will hear more about it this afternoon. But now I said, well, this was one of the big questions in the area, and often when a big question is solved, then somehow you would say, okay, now what else is to do? And so maybe the solution of the big question is just closes the subject somehow at the end. So I would like to convince you that this is not the end of the story. So there is still a lot to do in iteration of entire functions and in about the escaping set. So, and there are many, many questions that remain. And the aim of this talk is to present some of these questions. So, some question immediately come up with the resolution of Alex's original question. So, there is a counterexample, but you can still ask, does his conjecture hold in some reasonable classes of entire functions, well, whatever you find a reasonable class is, of course, but I think most people working in entire functions or meromorphic functions would say that functions of finite order is a reasonable class. People working in dynamics would probably say, well, I will say in a second what finite order is. There is also the so-called Yeremenko-Lyubich class. I will also define it in a second. So or the so-called Speiser class. So for people working in dynamics, they will also say these are very reasonable classes somehow to look at. So let me give the definitions here. So a function f is said to be of finite order if there is a number mu such that mod f is less than the exponential of mod z to the power of mu for large z. So f grows slower than the exponential of some power of z. So if this holds, then you say the function is of finite order, and the infimum of these exponents mu that you can take, this is called the order and denoted by rho of f. For these classes B and S, so we need a definition. Let thing of f inverse be the set of singularities of the inverse of f. So what are the singularities of the inverse? Singularities of the inverse are either critical values. So the simplest example is a function z squared. If you look at the point 0, well, then in the neighborhood of 0, you cannot take inverse. So the inverse of z squared is root z, but this has a singularity at 0. The second type of singularity of the inverse is the asymptotic value. Here, the prime example is the exponential function. Look at the exponent. So what is an asymptotic value? An asymptotic value is a value, you have a curve going to infinity. And if f of z tends to a value a, z tends to infinity along the curve, then a is called an asymptotic value. The example is the exponential function. Your curve is a negative real axis. And if you go to infinity along the negative real axis, then the exponential function will go to 0. And indeed, 0 is a singularity of the logarithm. It's the inverse of the exponential. So, and there are two classes now. One is a class which was introduced by Alex together with Michel Lyubich, is a class B, where the set of these singularities of the inverse is bounded. And they said that a subclass, namely where the set of singularities is finite, had been considered earlier already by Speiser and also others. So they named it after Speiser and called it Speiser class. And the class B is nowadays named after them and called Yeremenko-Lyubich class. So I should mention here a result by Roddenfuss, Rückert, Rempel, Schleicher from 2011, and also Baranski 2007. So Baranski has this for what's called disjoint type maps, and but this was sort of independent. Anyway, they show that a stronger form of Yeremenko's conjecture holds for functions which are in the class B and of finite order. The stronger form is not only that the connected components are unbounded, but that the stronger form is that every point in the escaping set can be connected with infinity by a curve in the escaping set. So if this is the case, then of course the connected components are unbounded. So they first proved in the paper that this stronger form doesn't hold in general, but they proved it then that it holds for, yeah, under these conditions, functions in the Eremenko-Lubitsch class of finite order. So this also is a reason why you could say, okay, here you have n. You put an or here. Does at least the original Eremenko conjecture then hold? But so this is these are questions which are open. And well, let's move to another question. Let's recall Alex's proof again. How to show that the escaping set is non-empty. So we were looking at points near points of maximum modulus. So a point of maximum modulus is a point where the function takes a maximum. So we are looking at points which are close to that. The function is still very large. So we are looking at a sequence of points where the function is always very large. So this implies that the function that iterates fn, that this tends to infinity very fast. There is actually a formal definition of the so-called fast escaping set. I do not want to give here, but clearly somehow follows from the proof that it tends to infinity very fast. You can ask whether there are also points where it tends to infinity slowly. And this was a question answered by Phil Rippon and Menestallert. They proved there are points which tend to infinity arbitrarily slowly. And well, it means given any sequence an tending to infinity, as slow as you like, there are points which tend to infinity slower than this sequence an. So now we introduce another concept here. So let f be entire R bigger than 0. You look at a connected component of the set where mod f is bigger than R. Such a component is called a tract. So, and I have a version of Wiemann-Walliron theory together with Phil and Gwyneth, which well applies the functions not only to entire functions, but applies to functions which are defined in tracts. And using this version, you can show that there are sort of points in the escaping set which go to infinity and stay in always in the same tract. Say, talking about tracts, say for example, take your R to be bigger than 1, and take your function f to be the sine function is less than 1 on the real axis. So it has two tracts, one in the upper half plane, one in the lower half plane. So the function has two tracts. So this result would say, okay, there are Alex's result that there are escaping points, that there are points in I of f. It would just say there are points going to infinity. You have no information whether they are in the upper half plane or lower half plane, and usually they would somehow switch, sometimes be in the upper, sometimes be in the lower half plane. This result would say, no, you can also have points which go to infinity only in the upper half plane or only in the lower half. But actually, you could also show there are points which somehow alternate between upper and lower half plane in any prescribed fashion. So, but what these points is a modification of Alex's method, so they also escape fast. So the question is, given a tract D, do there exist points which escape arbitrarily slowly in D? Well, if you take specifically the sine function, you could, well, the answer is yes. But if you have any entire function, say, which has two tracts, so this is open, there are results by James Waterman. So one condition is, so if the function is in this Yeremenko-Lyubich class, then the answer is yes. For example, this would apply to the sine function, which is in this class. He also has a general condition for functions outside the class. So he has a certain geometric condition, which I maybe don't want to state here. So we have seen here this question can be solved for the Yeremenko-Lyubich class. We saw in the previous slide also the Yeremenko-Lyubich class helps. So let me perhaps try to explain why is the condition that you are in the Yeremenko-Lyubich class so helpful. And the idea is the following. You take a large disk. It is so large that all the singularities are contained in the disk. So remember the class B, Yeremenko-Lyubich class B is defined as a class of functions where the set of singularities of the inverse is bounded. So it is bounded. You can find a large disk so that they are contained in the large disk. So well, you also take the radius of the disks so large that it's bigger than f of 0. So then you consider the outside of the disk and then the pre-image here. So there are no singularities when you of the inverse from right to left. Now you take the pre-image of this under the exponential function. Well, and essentially what you then do is you show that if you start in the half plane from here, go down here with the exponential, then with the inverse, and here the logarithm, then there are no singularities. So you can lift this and get a function capital F here so that this diagram commutes, and this function capital F is invertible if you restrict it to some of these. So this F is called the logarithmic transform. So this is univalent on any component here, say on this strip or on this strip. So it is univalent there. So, and then you can use all sorts of tools from the theory of univalent function, Koebe one-quarter theorem, Koebe distortion theorem. And so you have a lot of control over these functions. So this is why it is so helpful. And should also say that this was introduced by Alex Yeremenko and Michel Lyubich to transcendental dynamics. So it has been extremely powerful tool. So they used it to show that F is in the the class now called Yeremenko-Lyubich class. Then the escaping set is in the Julia set. So it means the escaping set has no interior points. So the escaping set equals its closure. So the escaping set has no interior points. So let me now come to another circle of questions, and there are a number of questions which concern the size of the escaping set. And well, by size, what do I mean by size? Well, it's dimension. It could be Hausdorff dimension. It could be packing dimension, and or Lebesgue measure of the set. So there are many results, but also many questions about dimensions and measure of the escaping set. So, well, let me start with here perhaps the easiest to phrase question. Is the packing dimension of the escaping set always 2? So, well, there are results. Rippon and Gminestella proved yes, if you are in the Yeremenko-Lyubich class. So, and well, not surprisingly, perhaps they also use the logarithmic change of variable. But well, I myself, I have a bit more general result. Well, the condition is, well, it's terrible. So, well, first we have MRF is the maximum modulus. This is the maximum on the circle of radius R. And then we have a condition that log MRF goes faster than log R. So, well, let us compare this condition with the definition of the order. I gave the definition of the order already, but if you rewrite the definition of the order in terms of this maximum modulus, then the definition of the order is that the order rho of f is the limb sup of log MRF over log R. So what are the differences? Well, one difference is you have a limb sup here and a limb inf here. But actually, the quantity downstairs here, you can also consider with a limb inf. Then this is known as a lower order of the function. So the main difference is that there are two logs here and there is one log here. It is actually known that if a function is in the Eremenko-Lubitsch class, then the order, and in fact the lower order, is at least a half. So if you are in the Eremenko-Lubitsch class, then the limb inf here is at least a half. So that actually shows that this condition is satisfied in the Eremenko-Lubitsch class, and so in some sense strengthens this result. In my view, this is a purely technical condition. So yeah, for some reason I needed it in the proof. I don't think that it has any real meaning. So well, it seems plausible that this holds also without the condition. But well, now let's talk about Hausdorff dimension and measure. So the first results here are by McMullen. He proved that for lambda e to the z, the Hausdorff dimension of the escaping set is 2, and that for cosine or lambda cosine plus mu with constant lambda mu, the measure of the escaping set is positive. But what is the idea here? Let's do the idea maybe for lambda cosine. Or say, let's do the idea for cosine. So the cosine is sort of bounded near the real axis, but it is large in the upper half plane and large in the lower half plane. So take some point, say far in the upper half plane. Similarly to what we had before, you take a small neighborhood of the point far in the upper half plane. This neighborhood will be mapped to a huge annulus. The annulus, now, well, most of the annulus will be, again, far in the upper half plane or far in the lower half plane, and only a small percentage of the points will be near the real axis. So you throw this away and then keep on doing this. So in some sense, you could say if I take some random point and iterate it, it will always be in the far in the upper or lower half plane, and chances to come near the real axis at some point are small. So, and they are actually so small that what remains is a set of positive measure. So this is what McMullen proved. And for lambda e to the z, this function is large in one half plane and small in the other half plane. So if you again think about point randomly wandering through the plane, at each step, chances are 50-50 that you are in the right half plane or in the left half plane. But this 50-50 chance is still good enough to give you Hausdorff dimension 2. So this is, well, in 2 lines, an argument of one paper. But
Can I have a question? For the first argument, the one about cosine,
yeah,
doesn't that argument show that the escaping set is really big? I mean, either infinite measure or even complement of finite measure?
yeah. So the true statement is that if you restrict by periodicity, either set must have infinite measure. So if you,
Yeah.
but but you are very close to the true statement. If you restrict say the cosine to one period strip, then the non-escaping part in this period strip has finite area. So yeah, so the escaping sort of is much larger. So, but the general idea is if your function f is large on a large set, then the escaping set should also be large. So sort of same idea. Think about a point randomly going through the plane, and if it lands where the function is large often, then this should be a large escaping set. So what are conditions which say that a function is large on a large set? One statement of this type is a theorem of Fragment-Lindelöf. It says, if you have a function which is bounded outside a sector of opening angle alpha, then the order is pi over alpha, at least. And there is a so-called theorem, there's a theorem of Donjoy-Kalaman-Alfors, which is an extension of this, say, to more general domains and sectors. But essentially, the statement is that if a function has finite order, then the function is large on a domain which, at least in some average sense, has the size of a sector. So this is the statement. So you could hope that maybe finite order functions also have a large escaping set. And this is true. This was proved by Hendrik Schubert and Krzysztof Baranski. So if function is in the Eremenko-Lubitsch class and the order is finite, then the escaping set has Hausdorff dimension 2. And well, together with Bruno Karpinska and Ministella, we proved a slight sharpening of this. Well, maybe don't look at this too closely. You have this really terrible limb soup here, but somehow, if the function has, you can convince yourself, if the function has finite order, then this limb soup here is 1, and then you have 2. So then it is a slight strengthening of the previous result. But let's come to the question. So the question is the hypothesis Eremenko-Lubitsch class necessary? So, I wanted to, so again, here, look at their result here. So they say if the function is in the Eremenko-Lubitsch class and of finite order, then so is this hypothesis necessary? In particular, is the Hausdorff dimension the escaping set whenever the order is finite? Well, I don't know. And now, if the order is small, even more could be true. If the order is less than a half, so then possibly we even have that the measure of the escaping set is positive. So what is it? Why is 1/2 boundary? If you think about the Fragment-Lindelöf theorem I showed you, well, if somehow the function is bounded outside a sector of opening angle alpha, then the order is at least pi over alpha. What happens if alpha is 2 pi? Then you are at order 1/2. So somehow these functions of order 1/2, there certainly there are many circles where the function is big. So these functions are somehow small, only on a small set. So I have no idea, but even if the answer to this is negative, so you can still ask, is there any growth rate which implies that the measure of the escaping set is positive, or at least that the dimension is 2? So, well, if this is not true, do we perhaps at least have this for functions of order less than 1 or order 0, or functions which grow like log r squared or whatever? I have no idea. There are some results I'm not going into now, which say the answer to these questions is yes, if the growth of the function is sufficiently regular. Whatever sufficiently regular means here, but I mean, there are some partial results to that effect. Well, for examples, for functions of completely irregular growth, for those who know what it means, there are such. Well, let's go back to this paper of Yermenko and Lubitsch. They considered periodic components of the Fatou set. So the Fatou set is a set where the iterates are in the family, and they called them Baker domain. Actually, Baker was not the first to show that such domains exist. This was done by Fatou already, but Baker proved various results about them. So called them Baker domain. And as I already mentioned, they showed that if you have a function in the Yermenko-Lubitsch class, then the escaping set is contained in the Julia set. So then there are no Baker domains. In other words, if you have a function with Baker domains, it is not in the Yermenko-Lubitsch class. So if you have a function with Baker domains, the set of singularities of the inverse is unbounded. And this was sharpened by Detlef Barkman, who proved that if the function has an invariant Baker domain, then not only the set of singularities of the inverse is bounded, but there is a constant k such that every annulus r less than mod z less than kr contains a singularity of the inverse. And so it's not only the set is unbounded, the set has a certain density. And here the question is, how sparse can the singularities really be? So it has to have a certain density, but what is really the density? On the other hand, so there is an example by Dominic Fleischmann. He has constructed an example with an invariant Baker domain where the singularities form a sequence which behaves like n squared. But by in Barkman, he says, well, it has to be denser than some geometric sequence. But there is a big gap between k to the n and n squared. So what is the right thing here? I have no idea. Well, talking about Baker domains, I cannot resist to state another question. So by Phil Rippon and Stellar, actually for all, I'm not, also what's the other questions, I'm not claiming that these are questions that I post somewhere, but they have been around somehow. So let U be a Baker domain. A Baker domain is a domain where the iterates go to infinity. If you have such a domain where the iterates go to infinity, is there any point on the boundary where the iterates go to infinity? Well, it seems maybe unreasonable to believe the opposite, but well, unless it is proven either way, well, we don't know. They showed that for wandering domains, the answer is positive. So if you have a wandering domain in the escaping set, then there are pointing. But for Baker domains, this is all. Well, finally, the Yermenko conjecture was on the topology of the escaping set. If you like topology, let me also ask two questions. Both are also due to Phil and Gwyneth. And so if the escaping set is disconnected, so there are examples where it is disconnected, but if it is, so there are examples where it is connected, there are examples where it's disconnected, but if it is disconnected, does it have uncountably many components? So I don't, well, this seems to be open for a while. Well, the other thing is, in the examples where it is connected, so usually the examples we have, when you have larger and larger curves, so the examples we know, there are usually larger and larger curves, which are contained in the escaping set. So larger and larger curves surrounding zero. Whether something like this must be true in general. Again, it is not, no. So whether the complement can contain an unbound. Well, and there are many, many more open questions, but I should leave at least 3 minutes to give you the opportunity to answer. So I should say, well, together with Lasse Rempe, we are writing currently a survey on the escaping set. Well, and hopefully soon you will find in this survey some more information about this question, but also many, many more open questions. So, and well, that's thank you very much for your attention. And Alex, happy birthday! We're very sorry that you cannot be here, but still, I hope you can enjoy the conference. Okay, all the best.